then the airspeed is going to be very high across the ground. The car is dragging air with it.
Yeah.
Okay?
The unseen
Okay, it's dragging air with it. So that will create a partial pressure upwards because moving air has lower pressure than stationary air. And what did I hear? At one of the races, a car drove so fast down the street, it sucked up one of the drain covers and hit the bottom of the chassis.
In Vegas, they hadn't sealed it properly to make sure it stayed where it was put.
Okay, because underneath the drain is regular air pressure.
Yep.
And fast moving air is lower air pressure. That's very Bernoulli. And so if you have a difference in pressure, watch out.
We were looking at Carlos Sainz's car, the Ferrari, and it was he who had one of these drain covers pop as he drove over it.
So why does what we casually call empty space have the power to push on planets, spacecraft, and even entire galaxies? On Earth, forces usually come from things you can feel. Air pushing on a wing, water pushing on a swimmer, a high-pressure region flowing toward a low-pressure one. Pressure is just force spread out over an area, and differences in pressure make air and water move, which in turn push on objects. Space, by contrast, seems like the opposite. Almost no atoms, almost no gas, just a vacuum. Yet a spacecraft with a big, shiny sail can actually be accelerated by sunlight alone, because light itself carries momentum, an ability to transfer motion, even though it has no mass in the ordinary sense. That is the first clue that emptiness is doing more than nothing, and it points directly back to our question. Light is not just illumination, it really does behave like a stream of tiny bullets. In physics, those bullets are called photons, and each photon carries a small amount of energy and momentum, so when photons bounce off a surface, they transfer a tiny push. This is called radiation pressure. If you imagine a spacecraft tens of meters across, covered in a thin, reflective film, the constant stream of solar photons can gradually change its orbit, the way a very gentle but never-ending wind can move a sailboat. We see the same process in comets. Their tails do not simply trail behind them, they're pushed roughly away from the sun by sunlight and by the solar wind, a fast stream of charged particles. So even in regions that look empty to us, fields of light and particles fill space and can exert pressure, bringing us closer to understanding how nothing shapes motion. But what if we turn off all the lights and pump out almost every last atom? Does the vacuum then finally become truly empty? According to quantum field theory, our best framework for describing particles, the answer is no. Even what we call a vacuum is a restless state where fields, the basic ingredients of nature, still fluctuate slightly. A field is something that has a value at every point in space, like temperature on a weather map, and in quantum physics, even their lowest energy state is not perfectly still. A striking demonstration is the Casimir effect. If you place two uncharged metal plates incredibly close together in a vacuum, they feel a tiny attractive force, because the quantum fields between the plates are restricted compared to the fields outside, leading to a small difference in vacuum energy that has been experimentally measured. That means empty space stores energy in its very structure, and energy, as Einstein showed, is intimately tied to gravity and motion. Einstein's radical move was to say that gravity is not a force pulling through space. It is the shape of space-time itself. Space-time is the combined fabric of 3 dimensions of space, plus 1 of time, and massive objects like stars and planets cause it to curve, so that what we perceive as gravitational attraction is really objects following the straightest possible paths in a curved geometry. In the mathematical description of this idea, called general relativity, it is not just energy density, the amount of energy per volume, that curves space-time, but also pressure and stress. Inside extremely dense objects like neutron stars, the pressure is so enormous that it significantly increases the star's gravitational pull, helping to keep light and matter tightly bound. So, if the vacuum itself has energy and pressure, general relativity says that this background will also help determine how everything in the universe moves. So, what kind of pressure of nothing could make the entire universe speed up, instead of slowing down under its own gravity? When astronomers measured very distant exploding stars in the late 20th century, they expected to see expansion gradually slowing over time because gravity from all the matter in the universe should pull things together. Instead, they found that the expansion is accelerating. Distant galaxies are receding faster and faster, a result that has been cross-checked by multiple independent observations of galaxies and the cosmic microwave background. The simplest way to explain this within general relativity is to say that space itself contains a nearly uniform energy, often modeled as vacuum energy, with a strongly negative pressure, more like tension in a stretched rubber band than pressure in a balloon. In Einstein's equations, this combination of positive energy density and negative pressure leads to a repulsive gravitational effect on large scales, and we give that phenomenon the name dark energy. The deep answer, then, is that emptiness is an active player in the cosmos, not a passive stage. At small scales, we meant pressure as a difference in airspeed lifting a wing. Then we saw radiation pressure from photons nudging spacecraft. Then we found that even the vacuum between metal plates has measurable energy. General relativity elevates all of this. It says that wherever there's energy or pressure, whether in air, light, or vacuum, they help determine the curvature of space-time, and that curvature guides the paths of planets, stars, and galaxies. So, when we say empty space is pushing galaxies apart, we are really saying that the energy and negative pressure of the vacuum are shaping the geometry of the universe in a way that makes distant objects accelerate away from each other. The philosophical twist is that when you strip the universe of matter and radiation, what remains, the structure of space-time itself, still has properties that decide the cosmic story. And why those properties have the particular values they do is one of the deepest unsolved questions in physics. Like, if this was interesting, hit the subscribe for more and turn that notification bell on.